Well, someone should be using math to do what we do in a library. I've talked to librarians, and they tell me what they do. They buy all the books that you want to go check out, and they discard the books that nobody wants. If you can imagine this wall behind me with all its vertical lines, instead of picturing them as vertical lines, imagine that they are books on a shelf. Each one of them has a width. How would you decide which of all those many books that you've got in front of you you're going to get rid of? That's what they call collection management. Just as a question, how many people in here have been in a library within the last year? How many people have a library card? Quite a few. You imagine among smart people, some people will want to have books. So, what is collection management? A librarian pulls a bunch of books off the shelf and says, I know how many times this thing got borrowed last year, and I know how many times it got borrowed the year before that. Is it going down? Is it going up? Is it more popular? Is it less popular? Should I keep it? I don't have enough space on my shelf to keep everything, so I have to buy some new things that are popular, and I have to get rid of some things that are not. I've talked to a librarian who specifically handled emails where people said, could you buy this for me? She would look at the thing and say, well, maybe I should send it to the library where they wanted it, maybe a couple of others that might not have this kind of thing. I was surprised how subjective this is. A library can have 1 million books in it. How are you going to handle all those on such a subjective basis? Why weed? By the way, the word weeding implies you're getting rid of books that nobody wants, as if you are weeding a garden. That's what they call it. I don't know why. How are you going to handle 1 million books on such a subjective basis? I thought I would come up with a model, which is a mathematical model that could tell you objectively what to get rid of. What does my model look like? I have the idea that you start with the molecules of the thing, the books on the shelf. It's either in and on the shelf, or it's out. That's my brilliant idea. There's my model. There's more to it than that, though. Obviously, if it's in today, it can be out tomorrow. If it's in today, it can be in tomorrow. Is it going to stay? Is it going to leave? Gives a couple of possibilities. In today, in tomorrow, in today, out today, in tomorrow, out today, in tomorrow. So how do you find those numbers? I'll get to why, but let's just start with the model. If you knew this, if you knew that you could flip an unfair coin and it would tell you whether the book is in tomorrow or out tomorrow, then you could predict how often it's going to stay on the shelf. Now, of all of you who said that you have a library card, how many of you have something borrowed on that library card right now? 2? Do you know that there are thousands of other people in this valley who have something checked out? If they all brought it back right now, the library would not have the capacity to keep all those. That's why we would want to know whether it's in tomorrow or out tomorrow. We don't have enough space on the shelves. So that's my model. It moves in and out. We can apply this idea to the books that are physically on the shelf. It keeps going. If it's in today, it can be in or out tomorrow, and it can be in or out the next day. Imagine you can flip a coin and it says 50% of the time, if it's in today, it will be out tomorrow. 50-50. But if it's out, it's 3/4 and 1/4, those two probabilities of being in and out. So what's the probability of it being in 2 days from now? You have to multiply all those lines together and then add them up and say how many of them are in, how many of them are out. This could be extended one day after another, after another, after another. If you keep drawing this tree, it could take a long time, but you can explain it succinctly if you just make a matrix. Mathematicians like those things. The top would say being in today. The bottom would say being out today. The left would say in tomorrow. The right would say out tomorrow. So each one of those has a probability. The top row has to add up to 1. The bottom row has to add up to 1, because the probability of something happening is 1. Multiply the matrix by itself. You get the probabilities for the next day. Multiply it by itself again the next day. Do this for 365 times with a computer, and you get the probability that this thing is going to be on the shelf or off the shelf on a day 1 year from today. I did this with a spreadsheet. It turns out, oddly enough, that it doesn't matter whether it's in or out today. The probability is still the same in a year. They tend to converge. And so you get this very nice model that says in today doesn't matter, out today doesn't matter. In a year, this is the probability it will be on the shelf, and this is the probability it will be borrowed. So how do you find these numbers? You still need to know how wide the thing is. A very big book takes up a lot of space on the shelf. But given the number of days it stays shelved, if it is shelved, and given the number of days that it stays borrowed, if it is borrowed, we'll tell you what all those numbers are that you should plug into the spreadsheet. And then you use the law of large numbers. It tells you how much space the books that you have are going to take up. If they're too big, you need more shelf space. If they're too small, you're okay. So I've got 2 minutes. There's one other part. You might say the future of libraries isn't books. Why do we need those? We've got eBooks. From your perspective, you go to the library and they say, yes, you can have it, or no, you can't. Why would we say, no, you can't have an ebook? Guess what? They work the same way. We still have to buy from the publisher the access to so many books at a time. The publisher says, you can only have so many people checking out this thing at a time. So instead of shelf space, what you've got is a budget. And instead of people checking things out manually, you have them doing it digitally. So once you've checked out 3 of them and you've only purchased 3 of them to have access to, the 4th person says, oh, I have to wait. How much time do you have to wait before somebody asks for it? There's a probability. This probability is modeled by something called an exponential distribution. It decreases with time. The longer time goes, the more likely it is that somebody has checked it out. You don't have to wait that long. I made another model of this based on the cost per book, how many requests per year, which tells you, based on what you're willing to spend on these things, how many can you buy, how long is the wait list going to be. I assume that you want the shortest wait list possible, given your cost. And I found out you can. You can model this. There are a couple of interesting findings. Something that checks out much longer makes much less of your shelf space that you need to accommodate. 4 times as long checked out means you only need to accommodate about 1/3 of the shelf space of the books that are required. Oddly enough, the length of the book didn't have a whole lot of influence on it, but I realized 10% is 10%. Percentage is the same. The number of days that you check something out, or the number of days it stays on the shelf, drastically changes the percent of the width of the books that you need to accommodate. Findings for eBooks are interesting. If you just buy one expensive book or buy a couple of others that are not so expensive, it makes very little difference in the waiting time. You should buy books that check out every 7 days, every 12, and every 365. It doesn't matter. As long as you buy things that check out, they can be big. The whole point of this is that a library that manages millions of things would like to have something more predictable. And I found a model that's just a beginning of the predictability that librarians can imagine. Thank you. Any questions? Yes. Well, I have only run simulations. I would like to find actual data in a library. It would be very useful. The only difficulty is that you would have to gather data for very many books. It can take a lot of server space, I imagine. How useful? You can write a program. There are programmers in libraries who can extract all the data from the records. This would work. It's just that it's ready to use. You can. There are a lot of other variables that a librarian would like to take into account, like does it get lost? You have to consider the probability that it gets lost. You have to consider whether something is water damaged. Everybody keeps looking at the shelf and saying, oh, well, that's really got wavy pages in it. I don't want to check it out. There are other things like that. But it's the beginning that at least has a simple model that it will be checked out or not. So it's a full model. It just doesn't take a lot of variables into account yet. Yes? It is in a database. Any librarian has access to the statistics for any one book they look up. And they say, this is how many times the thing checked out last year. This is how many times it's checked out to date in the current year. Those statistics are standardly kept. Yes. That's why I thought of just those things, because I thought, well, why not come up with a model that explains it and gives you a way to predict a variable that nobody thought of predicting yet, which is how much shelf space or what the waiting time is for an ebook.
So you work for a library. Have you approached the librarian about this?
I've tried to. I hadn't quite developed this model in a time when I would approach someone, but I want to do that, yes. So the short answer is yes, I plan to. It works best probably for a public library. An academic library might be a bit different because things check out once a year. But that might be worth trying to find an adjustment that would work well for an academic library too. Others? Yes?
Do you know why the spine width actually didn't end up entering your model?
Well, when I first made that slide, there was one thing I didn't realize that I said, well, 10% of 10 centimeters and 10% of 1 centimeter are different lengths, but they're still the same percentage. What I had in that slide was that column that says shelf means is that you need to accommodate 95% of the sum of widths of the books by your shelf. So that should be the same, but I ran other things in the simulation that said if you have a lot of very wide books, as long as they check out a lot, you don't need bigger shelf space. Yeah. Explaining why, I can't always explain why. It's just you run the simulation, it says that's what the number is. That's why these things are not really intuitive, are they? I mean, you have to plug in the numbers and have the calculations go through a whole bunch of server space, and you're done. You don't know why, you just run it. Any others? Yeah. I used Excel. I tried it with MATLAB. For some reason, I couldn't get a matrix to work right. But you know, it's just a matrix that runs over and over again. The ebook one is a bit different. I had to say everybody checks out the thing the same amount of time, 21 days, because that was a bit harder to simulate. I could come up with the math. I thought, well, the math was getting not so deep but complicated that I didn't think it would be easy to explain to an audience in the time frame. But I used Excel, simulated in both cases. This has to do with just imagining that the library is one enormous shelf and saying how much space do you need to accommodate in all of them. I didn't take the idea of a branch into account, but you can just say, well, all of these belong into the shelf that is this branch. So you can immediately place it into application in one branch. Yes, but I just imagined the library as one enormous shelf, which obviously isn't the case.
Thank you very much.
Thank you.